The SBSA Planetary Gear Sphere, cone gears on a globe, 3-level Wreath products, and recovered instantaneous addressing. Spheres of cones as meshing gears times the globe that carries them rotates 360 degrees times the Rubik lattice turns the whole. Cattell. Fifth in the SBSA series, synthesizes, sphere lattice, 3-axis spin, sphere cube, corrective note on instantaneous recovery. Abstract. The field sketch shows a configuration richer than any prior paper in this series. Small cone-bearing spheres arranged on the surface of a larger globe, like planetary gears on a ball, and the whole globe itself able to rotate 360 degrees about all 3 axes X, Y, Z. This arrangement then sits at each node of the 3x3x3 Rubik lattice. We formalize this as a 3-level nested structure. At the innermost level, each cone sphere is a single SBSA address with its own cyclic spin _n. At the middle level K, such cone spheres are arranged on a carrier globe, and gear meshing between adjacent spheres imposes a mechanical coupling constraint, reducing the naive product group _n_K to a proper subgroup, the gear constraint quotient, while the globe itself contributes an independent 360 degrees global rotation _globe. At the outer level, the Rubik lattice acts on the 27 carrier globes, contributing the full Rubik group _Rubik. The combined group is a 3-level Wreath product. Crucially, we prove that instantaneous address recovery. The O1 history-independent property established in 3 and partially surrendered in 4, 5 is fully recovered in this model for the vast majority of addresses, because the gear coupling constraint dramatically reduces the free degrees of freedom that generated the histodependence problem in the prior papers. Section 26. Reading the sketch. 3 nested levels. The new sketch shows 5 distinct drawings, each revealing one aspect of the structure. Top left, hatched cube, the original SBSA hypercube address space H, the foundation all papers share. Center top, ring of small spheres, labeled sphere of cones, 360 degrees X, Y, ZK, small cone spheres arranged around a torus equator, each capable of its own spin. The 360 degrees X, Y, Z annotation means the whole ring arrangement also rotates as a unit about all 3 axes. This is the middle level, a carrier globe holding K cone gear spheres on its surface. Top right, globe outline enclosing the cluster, 360 degrees X, Y, Z, the same cluster viewed as a full sphere, confirming the arrangement is spherical, not just toroidal, and the outer 360 degrees refers to the carrier globe's own global rotation independent of the individual gear sphere spins. Bottom left, 3x3 grid of these globe clusters, with small spheres at every junction, the Rubik lattice. Each node of the 3x3x3 grid is now one full carrier globe with its gear sphere cluster. The small spheres at junctions are the contact points between adjacent globes, gear mesh points that couple neighboring globes' rotations, exactly as planetary gears couple at their tangent points. Bottom right, twisted ribbon and Mobius strip shape a schematic of the Wreath product group composition, the twist of the outer permutation acting on the inner group, exactly the structure of equation 19.2 of the previous paper 5, here made literal in mechanical form. L1 innermost, each cone sphere, _n spin on its own axis. L2 middle K gear spheres on a carrier globe plus _globe, full 360 degrees of globe. L3 outermost 3x3x3 Rubik lattice of carrier globes, _Rubik. Section 27. Level 1, the cone gear sphere. Each small sphere on the carrier globe's surface carries n cone slots arranged azimuthally, as in definition 2.1 of 1, n equals 4 pi omega from 2. Each cone slot holds one complete SBSA address tuple S, T, W, V, set membership symbol H. The sphere spins about its own axis, advancing V as a clock hand as established in 1, contributing a single cyclic factor. Definition 27.1 Cone gear sphere. A cone gear sphere is a sphere of radius r carrying n azimuthal cone slots, each holding one SBSA address, spinning about its own axis with spin group. Underscore gear equals underscore n, 27.1. Its outer surface acts as a gear. It meshes with adjacent cone gear spheres on the carrier globe via tangent point contact at radius r, transmitting rotation mechanically to every sphere it touches. Figure 1. Left, a single cone gear sphere with n equals 8 azimuthal cone slots, colored wedges, and gear tooth rim, dashed ring with bumps, spinning about its own axis. Right, 3 adjacent gear spheres in contact, purple dots mark the mesh points, opposite rotation arrows show the gear coupling transmission. Section 28 The gear coupling constraint and its quotient group. This is the central new mathematical object. Naively, k cone gear spheres acting independently would contribute a group underscore n, caret k of order n to the power of k. But neighboring spheres on the carrier globe touch at a tangent point, and at that contact point the surface velocities must be equal and opposite, the classical gear meshing condition. This constraint is not optional, it is a physical law of the mechanism. Definition 28.1 Gear mesh constraint. Let gear spheres I and j be adjacent on the carrier globe, sharing a tangent contact point. Let underscore I, underscore j set membership symbol underscore n be their respective spin angles, in units of one slot width. The gear mesh constraint between I and j is underscore I plus underscore j is identical to 0, mod n, 28.1. i.e. adjacent spheres must carry equal and opposite discrete spin steps. If one advances one slot clockwise, its neighbor must advance one slot anticlockwise. Theorem 28.2, the gear constraint quotient group. Let the adjacency graph of the k cone gear spheres on the carrier globe be a connected graph gamma. The subgroup of underscore n, caret k satisfying all pairwise gear mesh constraints, 28.1 is underscore gear caret k equals the underscore 1, underscore k, set membership symbol underscore n caret k underscore I plus underscore j is identical to 0, mod n, for all edges, I, j is set membership symbol gamma, of 28.2. For a connected bipartite adjacency graph gamma with bipartition A, B, this group is isomorphic to underscore n, with generator underscore I equals +1 for all I set membership symbol A, and underscore j equals -1 for all j set membership symbol B. For a non-bipartite gamma, the constraint forces n even and the group is underscore the n2. Proof. Bipartite case. Fix any vertex I underscore 0 set membership symbol A, and set theta underscore I underscore 0 equals m set membership symbol underscore n. Since gamma is connected, every other vertex's value is forced by the constraint chain. Neighbors of I underscore 0 in B must have theta equals m, their neighbors back in A must have theta equals m, and so on. The entire state is thus determined by the single parameter m, giving a group isomorphic to underscore n. Non-bipartite case. An odd cycle forces m plus m is identical to 0, i.e. m is identical to 0, mod n2, restricting m to underscore at n2. Remark 28.3, dramatic order reduction. The gear mesh constraint reduces the internal degree of freedom from n to the power of k, uncoupled, down to n, coupled, bipartite, or n2, coupled, non-bipartite, an exponential collapse. This is the same phenomenon that makes a physical clock mechanism work. All gears are constrained to a single degree of freedom, the time, despite having many moving parts. In the SBSA context, this collapse is what restores instantaneous addressing, as we prove in section 31. Plus m plus m plus m plus m plus m m m m m m set A, theta equals plus m, set B theta equals m, single parameter, M set membership symbol _n controls all. Figure 2. The bipartite adjacency graph gamma of 10 cone gear spheres on the carrier globe. Once M set membership symbol _n is chosen for one amberset sphere, every other sphere's spin is forced by the gear mesh constraint. The entire K-sphere system has exactly one free parameter. Section 29 Level 2, the carrier globe. The K-cone gear spheres sit on the surface of a larger carrier globe of radius r. The carrier globe itself rotates 360 degrees about all three axes x, y, z, a second, independent layer of rotation acting on the whole arrangement at once, distinct from the individual gearsphere spins. Definition 29.1 Carrier globe group. The carrier globe contributes a discrete global rotation group. Globe equals _m times _m times _m, 29.1. Where m is the number of discrete orientation steps per axis, chosen so that each step moves the gearsphere positions to the next nearest neighbor position on the sphere surface. A full 360 degrees about any axis consists of m steps. The globe rotation permutes which cone gear sphere sits at which position on the globe surface, exactly analogous to how a Rubik face turn permutes which cubie sits at which position. But unlike a Rubik face turn, the globe rotation simultaneously carries every gearsphere's own spin axis through space. So the gear coupling, 28.1, is maintained. The constraint is frame invariant. Lemma 29.2. Globe rotation preserves gear mesh constraint. A globe rotation G-set membership symbol _globe permutes the gearsphere positions, but does not alter any gearsphere's spin state. Therefore the gear mesh relation, 28.1, holds before and after any globe rotation. The constraint quotient _gear (k) is preserved under the _globe action. Proof. A globe rotation acts on position labels, which sphere is at which lattice site of the globe's surface, not on the spin angle register of each sphere. The constraint, 28.1, depends only on whether two spheres are adjacent, an adjacency relation that moves with the spheres under any permutation, and their relative spin values, which are unchanged by the rotation. Hence the constraint set is invariant. XYZ level 2 group _L2 equals _gear (k), approximately equal to _n, bipartite, right semidirect product _globe, approximately equal to _m cubed. Figure 3. Left, the carrier globe, translucent sphere, with 10 cone gear spheres on its surface, and 3 great circle rings red, blue, green, showing the globe's own 3 axes of 360 degrees rotation. Right, the level 2 group, the gear constraint quotient, _n, semidirectly combined with the globe's discrete orientation group, _m cubed. Section 30 Level 3, the Rubik lattice of carrier globes. Carrier globes sit at the 27 nodes of a 3 by 3 by 3 lattice. Face turns of the lattice rotate a 3 by 3 layer of globes as a rigid block, exactly as in section 18 of A5, and exactly isomorphic to the physical Rubik's cube group, theorem 18.2.5. The small spheres at every junction in the sketch represent the tangent contact points between adjacent carrier globes, a further mechanical coupling between the globe level rotations. Face turn F rotates right column of 3 globes as unit, globe contact cone gear sphere carrier globe center. Figure 4. The 3 by 3 lattice of carrier globes. Each globe carries visible cone gear spheres on its surface. Purple dots mark the globe-to-globe contact points at every junction. The gold globe, center, and green globe, top right corner, are highlighted. The gold arc shows a Rubik face turn rotating the right column of 3 globes. Section 31 The 3-level group, an instantaneous recovery. We can now assemble the full combined group, and prove the main recovery theorem. Definition 31.1, 3-level planetary group. The complete group governing the SBSA Planetary geosphere system is the three-level Wreath product. _PGS equals _gear _K right semidirect product _globe _Rubik 31.1. More explicitly, _gear _K approximately equal to _n bipartite case, theorem 28.2, and _globe approximately equal to _m cubed, definition 29.1. So the inner group per globe is _L2 equals _n right semidirect product _m cubed. The outer wreath wraps 27 independent copies of _L2 with the Rubik group _Rubik. Theorem 31.2, Instantaneous address recovery. For any address A equals X, Y, Z, S, T, W, V, set membership symbol lambda times H in the SBSA planetary geosphere, recovery is achievable by a computation of fixed constant size, independent of the total capacity L cubed H and independent of operation history, using at most 5 stored values per globe. Recovery is O1, in the strictest sense, the same guarantee originally proven in 3. Proof. The gear constraint quotient, theorem 28.2, reduces each globe's internal state to a single integer m set membership symbol _n, regardless of how many geosphere spins have been applied. All are determined by m. The globe orientation is stored as a triple, alpha, beta, gamma, set membership symbol _m cubed. The lattice position of the globe is given by the Rubik permutation state sigma, which is itself an element of _Rubik admitting a bounded representation, at most 20 face turns, 6. The 5 stored values per globe are therefore m, alpha, beta, gamma, sigma. Given these, any address is recovered as locate A equals sigma x, y, z, alpha, beta, gamma, oriented globe slot K, S, T, W, V, M, 31.2. Each of the 3 steps is a single O1 lookup or arithmetic operation, a Rubik permutation evaluation, globe orientation lookup, slot index formula from 1. The total operation count is bounded by a fixed constant independent of K, L, N, M, or H. The key insight is that the gear coupling is not a limitation to work around. It is the mechanism that collapses the exponential degree of freedom explosion that threatened O1 recovery in the prior papers. The non-bipartite 3-ring sphere of 4 had non-abelian generators at 6 pole slots, creating the histodependence of corollary 15.1 in 4. The gear coupling here eliminates that problem at source. Instead of each gear sphere having an independent spin variable that could accumulate an untracked history, all K spins are slaved to one master variable m, and only m needs to be stored and tracked. Sigma set membership symbol _alpha, beta, gamma m5 stored values per globe sigma x, y, z, globe site less than or equal to 20 face turns, 601 alpha, beta, gamma, cone gear globe orientation 01 slot S, T, W, V, M, gear master int MO1 address A recovered. Figure 5. The 3-step O1 recovery pipeline. 5 stored values per globe, sigma, alpha, beta, gamma, m, feed into 3 independent constant time operations, Rubik permutation lookup, globe orientation lookup, slot index formula, yielding the recovered address with no dependence on system size or operation history. Recovery summary, restoration of the title claim from 3. The prior paper, 5, showed, section 25 corrective note, that instantaneous history-independent recovery was narrowed, but not eliminated in the 3-ring sphere model. The planetary geosphere model here fully restores the strongest form of the claim for all addresses universally, not merely for a pole-free subset. Model. Recovery. History-independent. 4D twist, 3. Less than or equal to 4 twists, stride formula. Yes, all addresses. Single ring sphere, 1. 3 lookups plus offset. Yes, all addresses. Triple ring spin, 4. Offset, or group word. Only non-pole slots. Sphere cube, 5. Rubik lookup plus spin word. Only pole-free, non-turned. Planetary gear sphere, this paper. Yes, all addresses universally. Section 32 Total capacity, and God's number. Theorem 32.1, Total capacity. The planetary gear sphere system has total addressable capacity. _PGS times H equals L cubed times K times N times H equals 27 times K times N times 1.59984 times 10 to the power of 1, 32.1. Where L equals 3, lattice side, K equals number of cone gear spheres per carrier globe, N equals cone slots per gear sphere, and H is the SBSA hypercube capacity from 2. Theorem 32.2, Planetary gear God's number. Any state of the full system is reachable from any other in at most d_PGS less than or equal to 20 plus L cubed times M plus 1, 32.2. Moves. The bound 20 covers the Rubik lattice permutation 6. Within each globe, the gear constraint quotient means only one master spin variable M needs to be corrected, less than or equal to N 2 steps, plus one globe orientation correction, less than or equal to M 2 steps per axis, 3 axes, all bounded by M plus 1. Crucially, the exponential factor N to the power of K of unconstrained gears does not appear. The gear coupling has already collapsed it. Section 33 Conclusion. The field sketch introduced a 3-level structure. Cone gear spheres meshing on a carrier globe, the globe rotating freely 360 degrees about all 3 axes, and the whole assembly placed at every node of a 3x3x3 Rubik lattice. Formalizing this yields the planetary gear sphere model, whose group structure, definition 31.1, is a 3-level Wreath product, _n right semidirect product _m cubed, _Rubik. 2 results stand above the others. First, Theorem 28.2 proves that the gear mesh constraint is not merely a mechanical detail, but a group theoretic quotient that collapses the internal degree of freedom of K-coupled gear spheres from N to the power of K down to N a bipartite, or N to a non-bipartite. This is the planetary gear principle stated algebraically. Second, and most significantly for the overall series, Theorem 31.2 proves that instantaneous address recovery, O1, history independent, universal across all addresses, is fully restored. The partial loss of this property, identified in the corrective note of A5, was the price of the non-abelian spin structure in the 3-ring model. The gear coupling mechanism reimposes the abelian structure where it matters most, one master variable per globe, recovering the title claim of 3 in its strictest form, while retaining all the richer geometric and mechanical structure of the 3-ring and Rubik lattice models built across this series. References. Cattell, A. 2026. The SBSA sphere lattice, cone partitioned addressing on a grid of independent